Hello students, week 16 physics for grade 12, chapter 40 lesson 8 controlling nuclear fusion, textbook page 821 and 822. At the end of the lesson, you will be able to explain why thermonuclear fusion reactions are so difficult to carry out. Producing thermonuclear fusion reactions under controlled conditions requires temperatures of hundreds of millions of degrees. So, producing and sustaining such high temperatures along with reasonable densities is the goal of much current research. No matter how the temperature is produced, a problem is that all materials melt and vaporize at the temperatures required for fusion. So this is one of the main issue regarding dealing with nuclear fusion. One solution to this problem is to confine the reaction in a non-material container such as a magnetic field. You can see the figure here. A magnetic bottle is used for containing plasmas for fusion research. So a magnetic bottle is actually a non-material container. A magnetic field is non-material, can exist at any temperature, and can exert powerful forces on charged particles in motion. Magnetic walls of sufficient strength can hold hot ionized gases called plasmas. Magnetic compression heats the plasma to fusion temperatures. So this is one of the solution for obtaining and actually sustaining the high temperature. Because as we discussed in the previous slide, at high temperatures, most of the materials either melt or vaporize. So magnetic field as a non-material can be used to compress, or you can say to heat the plasma into a fusion temperature. At about 1,000,000 degrees, some nuclei are moving fast enough to overcome electrical repulsion and slam together, but the energy output is much smaller than the energy used to heat the plasma. At about 350 million degrees, the fusion reactions will produce enough energy to be self-sustaining. So this is another big problem. At this ignition temperature, nuclear burning yields a sustained power output without further input of energy. So if we can have such a ignition temperature like 350 million degrees, fusion reactions can give enough output. The state of fusion research. Fusion has already been achieved in several devices, but instabilities in the plasma have prevented a sustained reaction. A big problem is devising a field system that will hold the plasma in a stable and sustained position while a number of nuclei fuse. So this is the big problem actually faced by, or you can say still facing by the scientists, their research in this field. Another promising approach uses high energy lasers. So this is another technology. One technique is to aim laser beams at a common point and drop solid pellets of frozen hydrogen isotopes through the crossfire. So the resulting heat will be carried off by molten lithium to produce steam. In the pellet chamber at Lawrence Livermore Laboratory, the laser source is NOVA, the most powerful laser in the world, which directs 10 beams into the target region. A potential energy source. You can say fusion power is actually a potential energy source. Fusion reactors cannot become supercritical and get out of control because fusion requires no critical mass. One of the benefit. There is no air pollution because the only product of the thermonuclear combustion is helium, so no matter of air pollution. Disposal of radioactive waste is not a major problem. It was a big problem in nuclear fission. The fuel for nuclear fusion is hydrogen, in particular its heavier isotopes deuterium and tritium. So hydrogen is the most plentiful element in the universe. So we have enough fuel for nuclear fusion. Deuterium and tritium are found in ordinary water. So because of the abundance of fusion fuel, the amount of energy that can be released in a controlled manner is virtually unlimited. In the fusion reactions of hydrogen isotopes, most of the energy released is carried by the lighter weight particles, protons and neutrons, which fly off at high speeds. You can see in the figure, two hydrogen combine then form helium by removing one neutron. Again, you can see 1H2, 1H3. So these are the two isotopes of hydrogen that forms helium, and then again a neutron is released. The development of fusion power has been slow and difficult, already extending over 50 years. And you know the reason now why it takes time, or why it is still under process, or you can say in progress. It is one of the biggest scientific and engineering challenges that we face. Our hope is that it will be achieved and will be a primary energy source for future generations. So we hope that that will be the primary energy source for future generations. Can you answer this question? Why are thermonuclear fusion reactions so difficult to carry out? Try to answer this question. Thank you and see you next time.